Yeah. Yep. All right. So we started segueing at the end of our last class into reaction. Do you guys have them numbered?
Yes.
Reaction number 5, I think. I don't have any numbers.
I have this 4.
This was 4, formation of imines and enamines. What was number 4? Hydration.
Hydrolysis to gel.
Hydrolysis. Okay, that's good. That means that number 5 is what we're segueing into. Formation of imines and enamines. To clarify, the imine is what we referred to as a Schiff base. And if you can predict the formation of imines and enamines, that means you can also predict the formation of these oximes and hydrosomes. It's just a matter of what else is attached to the nitrogen reagent in the reaction with an acetal or hemiacetal. Oh, no, I think I did it wrong. Sorry. I think I wanted us to segue into acetals and hemiacetals before we, yeah. I thought something seemed off about this. We'll come back to these. I want to do that in a specific sequence because the reactions towards the front are going to be the reactions for the mechanisms we learn. All right, formation of acetals and hemiacetals. So I'm going to write a generic reaction. And we're going to look at the generic reaction for the hemiacetal formation. So this is a carbonyl, could be a ketone if R is a carbon group, could be an aldehyde if R is a hydrogen. And I'm reacting it with an alcohol. Now, specifically, we're going to react this with just one equivalence of alcohol in acidic conditions. Only in acidic conditions. We're not going to see this reaction in basic conditions. Underneath there, I have MS. And MS is an abbreviation for molecular sieves. Molecular sieves are porous materials. You can think of them kind of like being like ceramic. They just have a bunch of little tiny holes in it. The thing about molecular sieves is that those pores are so small that they only fit a molecule of water inside of them. The sieve itself is about 2.5 angstroms across. So it's very small. It won't fit a molecule of alcohol. It won't fit a molecule of an aldehyde. It will really only fit a molecule of water. This allows us to take advantage of Le Chatelier's principle, equilibrium principle, because one of the products of this reaction will be water, and this reaction is heavily dependent on equilibrium. So if we want to produce as much hemiacetal as possible, or acetal as possible, then we want to pull out any water that forms. Pull out a product, it's going to shift the equilibrium to form more products. Now I will say that some places you will see MS, some places you will see mole sieves written. In other places, you just won't see it at all, and it's just assumed that it might be there or not. So I'm not going to require that you have molecular sieves. I'm not going to require that you say MS on your reagents, but I want you to have some awareness of what we're trying to save from that.
So do we have to put MS for these reactions? I don't know if you said that.
I just said we don't have to.
Okay.
I will be doing it for your sake, but you don't have to do it. Deal? You don't have to, but you're welcome to. All right, now this is the formation of the hemiacetal, and excuse me, I forgot my R prime attaches here. If you remember, I refer to the hemiacetal as a geminal etherol. I've got an ether and an alcohol on the same carbon. If this intermediate, the hemiacetal, reacts with a second equivalence of alcohol in the presence of acid with molecular sieves, then the product becomes an acetal. And you can see that this is actually just a gem diether. Yeah?
What's the R, with the one?
R prime distinguishes R from R prime, different carbon groups. Not trying to say that what this is has to be this as well. So is this a ketone?
So that R would be the regular, the one without the prime.
Yeah, that's why it's R. And then R prime is just something else. And then R double prime is something other again. We could call it R1 or R2 or R3, but then getting subscripts makes it feel like, am I saying there's two of them? Am I saying there's three of them? It gets a little more confusing. Is this generic reagent a ketone? Doesn't have to be. If R is a hydrogen, then what we're seeing is the formation of a hemiacetal or an acetal on an aldehyde carbon or a ketone carbon. That happens equivalently. Now, I do think that we can break apart that word acetal a little bit. You guys remember this ACET prefix? We saw it in acetic acid, acetaldehyde, acetamide. This is that prefix for the 2-carbon carbonyl, acetonitrile. And then al is the suffix for what functional group? Aldehyde. So it's, I think the name here is meant to infer something about taking the carbonyl of an aldehyde and changing it in some way. It's unclear to me why they chose this name because it doesn't infer that it's turning into a diether. Now, IUPAC used to actually have two different names, one for the acetal from an aldehyde and one for the acetal from a ketone. And then they decided to group them under the same umbrella. And then actually more recently, they decided to try and split them apart again. So acetals are meant to come from aldehydes. Imagine what they call what comes from a ketone. An acetone, right? Which is actually where you get the name acetone, the 3-carbon ketone. No, they call it a ketal, which looks like the front half of ketone and the second half of, or also the front half of aldehyde. So we're only going to refer to everything as aldehydes because I don't think IUPAC has their priorities straight. And since they're naming something as wild as ketal, let's just not call it ketal. Okay. Before we get into example problems, because really that's all this is going to be, find the starting material that makes the product, find the alcohol that makes the product, or predict the product based on the alcohol and starting material. I want to talk about the usefulness of this. First of all, acetals react selectively with aldehydes and then ketones, which means that if I wanted to do a reaction with, let's say, a carboxylic acid or an ester that's in my reaction, I could actually do a reaction with the aldehyde or ketone, take them away from being ketones or aldehydes, take them away from being carbonyls, and then do some reactivity on a less reactive, a higher order functional group. Plus, if I have a ketone and an aldehyde, I can selectively react with the aldehyde first. And the way that we phrase this is it allows us to protect those carbonyls so that I can do other types of chemistry and protect them from something. So let me give you an example that highlights this protection. If I wanted to do a Grignard reaction, I want to turn this alkyl halide into a Grignard, and I want to, let's say, add formaldehyde so that I can just add a 1-carbon alcohol. What I'm going to do over the reaction arrow is say, first I'll add magnesium, which I think you guys would agree, the magnesium turns this into the Grignard. Then I'll add formaldehyde, and then I'll do my aqueous workup. We'd expect this carbon to become the nucleophilic carbon, and we would expect it to attack the carbon of formaldehyde. I would expect to have a 7-carbon chain when I'm done with this. So then, why is it, oops, sorry, one too many carbons in my chain. Why is it that I get this product? Plus, formaldehyde never actually reacts. The reason is, as soon as I add the magnesium and I turn this carbon into a Grignard, I now have both a nucleophilic carbon and an electrophilic carbon on my molecule. This just goes through an intramolecular acyl addition. I cannot form Grignards in the presence of carbonyls without expecting them to react. And this was an intramolecular reaction, but I think you would all agree that if I had a similar molecule that maybe couldn't react intramolecularly, and I wanted to do something similar, turn this into a Grignard, and then add a carbonyl, molecule 1 of this reagent is just going to react with molecule 2, and then molecule 2 will react with molecule 3, and I'm going to cause polymeration to occur. I'm just going to keep having Grignards attack carbonyls on neighboring molecules. So I can't turn this into a Grignard without it doing some sort of unwanted reaction. So how do I get the final product that I want then? Let's protect the carbonyl. If I want to go from this 6-carbon ketone chain, and I want to go to this 7-carbon alcohol, I'm going to map my carbons again so that we can keep track of what we're looking at. It's very obvious that I need to form a carbon-carbon bond. Carbon 6 to carbon 7 needs to form. I need to create an alcohol. Well, I can create primary alcohols by doing acyl addition to formaldehyde. But I cannot have a Grignard in the presence of that ketone. So I need to protect the ketone. The first thing that I will do is turn that ketone into an acetal. So I'm going to add methanol, 2 equivalences, with acid. I'll follow that by magnesium, followed by formaldehyde, followed by an aqueous workup. Now, because I know that's a lot of steps all happening at once, I'm going to show you guys the intermediates that form as we go. First, the ketone is turned into a hemiacetal. Second, the hemiacetal is turned into an acetal. Acetals are just ethers. Well, they're not just ethers. They're geminal diethers. That does give them unique reactivity to other ethers. But being ethers, they're not electrophilic. They're not going to act as leading groups. They're not going to do any sort of acyl addition. Then I can turn that halogen into a Grignard. Then I can add that alcohol. I'm actually going to stop here, and I'm not going to show the alcohol. I'm going to show the alkoxide that forms. We talked about this in our last unit. The benefit or the purpose of the acid step there is to protonate the alcohol. The thing is that when acetals are subjected to aqueous acidic conditions, H3O+, they hydrolyze back to ketones. I know you guys have a lot that you're looking at right now. I do want to point out a small thing. In this reaction to form acetals, I'm using H+. Is H+ necessarily dissolved in water? No, by definition, H3O+ requires water, but H+ doesn't necessarily require water. So by using H+ to form the acetals, I'm avoiding hydrolyzing the acetals. But by using H3O+, I am hydrolyzing the acetals. So in this last step, where I add H3O+, I'm doing two things. I'm protonating the alcohol, and I'm hydrolyzing the acetal back to a ketone. Okay, let's do some practice problems of using acetals. I'll have you fill in the reagent, the product, and the starting material for some of these. I do think, in all honesty, that the first one is probably the hardest. Doesn't make it impossible, just means that you might want to start by looking at what happens on the bottom. Honestly, yeah, I'd maybe look at the bottom one, try to solve that one first, then compare how the other two work. And because we don't have a ton of time, I'm only going to give you guys a handful of minutes to try and brainstorm these. Start looking for patterns. Look for some trends. Okay, this is not a bad thought. You took two alcohols and you attached them. But why couldn't the two alcohols come from the same carbon chain? So this could be one alcohol, this could be the other. And now maybe you understand what's happening here. Yeah, this is good. Yeah, I would have drawn it more with the. Yeah, but you got it.
Okay.
You got it right.
I don't know if that.
No, I won't do it because I don't see a CH3 group anywhere in this molecule. So instead, what you'll have to do is figure out where did that alcohol come from and where did that alcohol come from. And since they're attached, maybe they came from the same molecule. No methyl group. 3 bonds to an oxygen gives it a positive charge. You get rid of that, it's just a ketone. That's it. That's exactly it. so we don't have, yes, exactly. We don't have a lot of time, so let me give you guys the idea of how to break these down. I'm gonna go from the bottom to the top. The bottom looks like the ones we've just seen. Here's my geminal diether, correct? That's my acetal. A word to the wise, the acetal carbon is what carbon? The acetal carbon is your aldehyde or ketone carbon. Notice how that carbon has 2 bonds to oxygen, just like an aldehyde or a ketone does. So all you need to do is redraw your starting material and transform your acetal back into a carbonyl. Notice that that is a secondary acetal, meaning that acetal has 2 other carbons connected to it. That means it's going to be a secondary carbonyl, or in other words, a ketone. A primary acetal, and notice how it becomes a primary carbonyl, an aldehyde. So what we did here was we cleaved off the 2 oxygens that were attached. There is a byproduct of water that's formed in each of these steps. And it's actually, when we look at the mechanism at the end of today's lecture, we're going to see how it is the oxygen in water that was the original carbonyl oxygen. These oxygens come from the alcohols. So 1 equivalence of OCH3, 2nd equivalence of OCH3. 2 equivalences of methanol needed here. Up here, if I try to do the same thing, if I break these bonds to the carbonyls, here's 1 equivalence of alcohol, here's another equivalence of alcohol, and notice how that makes a 4-membered chain. 1, 2, 3, 4. I react this aldehyde with this reagent and acid, and I get a cyclic acetal. So my acetals can be 2 equivalences of 1 alcohol, or my acetals can form from 1 equivalence of a diol. And then that's what we see here. My ketone carbon is going to be the carbonyl carbon, and it's going to be connected to both oxygens from this diol, and those diols will all be connected to each other. So if 1 connected to 2, 3, 4, 5, 5 connects to the carbonyl carbon, and the carbonyl carbon also connects to 1, that's a 6-membered acetal ring. So 5-membered acetal ring, 1,2-ethane diol. 6-membered acetal ring, 1,3-propane diol. Or 2 ethers at the same position, that's just 2 equivalences of an alcohol. Now I also put up this short synthesis. Take a ketone and a carboxylic acid and reduce it to a ketone and a primary alcohol. What jumps out to you as an obvious solution or a reagent that definitely needs to be here? Sorry?
Something that can reduce like carboxylic acid.
We need to reduce a carboxylic acid. Carboxylic acids are not super reactive, so we need a strong reducing agent. We need LAH. True or false, reducing a carboxylic acid is also going to reduce a ketone. True. So could I reduce both of them and then selectively oxidize just the ketone? There's no way. Because oxidizing a secondary alcohol would also oxidize a primary alcohol. There's no way to prevent that. I don't have allylic regions or benzylic alcohols here. So what can I do? I can first protect my ketone, because ketones are more reactive than carboxylic acids. So ketones will form acetals, carboxylic acids won't. Now that my ketone is not a ketone, I can reduce the carboxylic acid that takes the carboxylic acid down to a primary alcohol, and then I just need to hydrolyze the acetal back to a ketone. Now, to be fair, some would argue that this H plus step, the aqueous workup after the reduction, could just as easily be that hydrolysis step. I would totally agree. But we can show it separately to show how the acetal is there to protect the ketone from being reduced.
And could we have also just done, instead of like the double alcohol, if we've just done like 2 equivalents of like
Yes.
1 CH3
Yes.
alcohol or something?
So in all transparency, what you want to use comes down to cost, what you have available, and how much time you want to spend. If you want to protect a carbonyl with 2 equivalences of alcohol, it's going to take longer to complete that reaction because now there are more individual molecules involved. If you want to complete it with a diol, it happens quicker because there are less molecules that need to find each other and go through the reaction. Stoichiometrically, a diol is also easier. You need less equivalences of a diol, 1 to 1, rather than 2 equivalences of just a monoalcohol. But then there's cost. We have methanol and ethanol available in our lab, in our stockroom, but I don't think that we have 1,2-ethane diol, and I don't think we have 1,3-propane diol. So we'd have to go out and buy those reagents, and that might be more costly than we want to do. But on paper, any 2 equivalences of alcohol works, whether those 2 equivalences are attached to the same carbon chain or whether they are just 2 equivalences of this. I want to say that in your written work, there's a problem, a synthesis that actually has both the ketone and the 2 alcohols all on the same carbon chain. And what you demonstrate with your mechanism is the formation of the acetal intramolecularly both times. You create a spiro complex, 2 rings that are fused at the same point because it's an acetal forming on the molecule. All of the reagent is present on the same molecule. You can do some really cool looking stuff with it. All right, any questions here about acetals and hemiacetals? We understand that they can be formed just as easily as they can be hydrolyzed. And that is what kind of creates the need for caution with the molecular sieves. Then again, molecular sieves, it's really not something that you want to, they're not the most fun to work with in acidic conditions. There is one last thing I want to say about all of this, and that is H+. H+ is the most ambiguous reagent that you will ever see in organic chemistry, because all it's saying is proton donor. It doesn't tell you whether that's in aqueous conditions or non-aqueous conditions. When we use H+ in forming acetals, it cannot be H3O+, because H3O+ hydrolyzes acetals, so it would reverse our reaction. Instead, H+ can be acetic acid, which we can abbreviate as ACOH. Or if you don't remember what acetic acid's structure is, its common name, or its IUPAC name is ethanoic acid, 2-carbon carboxylic acid. This could be toslic acid. Toslic acid, by the way, is just para-toluene sulfonic acid. There's a number of other organic acids that we could use. These would probably be the most familiar. The nice thing about acetic acid and toslic acid is that they have very obvious conjugate bases. Acetate and toslate are the conjugate bases of acetic acid and toslic acid. But do you know what is the conjugate base of H+? Nope. Exactly the opposite. It's actually on the board. I mean, like, I filled it in. It's there at the end of the arrow. Nothing is the conjugate base of H+, because a conjugate base is what's left over after H+ has been donated. So if you're showing in a mechanism that your proton source is not H3O+, is not ACOH, is not TSOH, your proton source is H+, then the conjugate base is nothing. And that's a little confusing when doing a mechanism, because we often use a conjugate base to show the deprotonation step. And there's no conjugate base. All right. As we continue on with our reactions, we're going to move on to 6. This is where we'll talk about the formation of imines, aka Schiff bases, enamines, and also the oximes and hydrozones. And I'm retiring. So first, let's look at the primary amine to the imine. I'm going to set this up similar. We're just going to look at a generic reaction, and then we'll do some practice problems. Very similar setup to the acetal and the hemiacetal, in that here we get the primary amine plus H plus and molecular sieves. The molecular sieves being present reminds us that what will be a byproduct of this reaction? Water will be a byproduct. If water is a byproduct and we want to make sure that it's removed, what is the concern about the product here?
It might react.
It can be easily hydrolyzed in the reverse reaction. So equilibrium is another important game here. So the final product that we get, oops, sorry. From a primary amine, we go to an imine, the carbon-nitrogen double bond. In order to form that carbon-nitrogen double bond, nitrogen has to lose both of its hydrogens, and the carbonyl needs to lose its oxygen. That's where we get our equivalence of H2O. H2O. Now the formation here is very similar. So there's a there's a place where you could maybe call it a hemiimine, and that's where there would be an alcohol attached to the carbonyl carbon and an amine attached to the carbonyl carbon. Now, we're not going to look at the mechanism for this one quite as much because it's just a lot of the same thing for acetals, but we'll be able to predict all of the intermediates based on a very similar mechanism. If we have a secondary amine, this leads to the formation of an enamine. So that means that I've got R prime 2 NH with H plus and molecular sieves. We said up above that the primary amine loses its 2 hydrogens, carbonyl loses its oxygen, that generates H2O. Can the secondary amine lose 2 hydrogens? It's only got 1 to give away. So where is the other hydrogen going to come from? Well, it's going to come from the formation of the alkene. It's actually going to come from an adjacent hydrogen. Or excuse me, it's going to come from an adjacent carbon. That generates my H2O. This goes from a CH3 to a CH2. And this is just a generic reaction, so this could just as easily have been a CH2 that goes to a CH and it's got another carbon chain on it. Or it could be a CH with 2 carbon chains and it goes to just a totally substituted alkene carbon.
Is there a way to know which way it's going to go, the double bond?
Whether it goes to the left or to the right? Yeah, it's going to form the most stable alkene, which is the most substituted alkene. That's about it. Yeah. Ultimately, this reaction involves a lot of positive charges, carbocation intermediates, so it will choose the most energetically favorable product. But you're not going to have to deal with that too much. The only reason that I don't show the double bond forming between the carbonyl carbon and the R group is because in a generic example, R can be hydrogen, making the carbonyl an aldehyde. And you can't form a double bond with hydrogen. Let's look at what happens when we use hydroxylamine to run our reaction. So rather than having a primary amine or a secondary amine, let's look at having a hydroxylamine. So that is NH2O2 with our same conditions. Once again, I generate an equivalence of H2O, but this time I don't have an R group attached to my nitrogen. It's not like I have methyl or phenyl or cyclopentyl or diethyl, diisopropyl. I just have hydroxyl. And then let's just swap this out one more time and we'll show how hydrazine gives us hydrazones. Now, a hydrazine needs to have an NH2 group plus an NN bond. And you know what? Yeah, I guess I could have been maybe keeping these things a little bit more consistent. I'm gonna just rewrite this a little bit. I'm gonna put NH2 because now it resembles NH2, NH, NH2. But now the R group is not just a carbon chain, it's actually going to be a nitrogen with two other groups. Remember that hydrazine is H2N, NH2. In that case, R prime is H. But R prime could be one H and one phenyl group, one H and one methyl group. So this second nitrogen can be anything, but the first nitrogen still needs to set me up to remove that equivalence of H2O at the end. So the product that I get here, I get my carbon-nitrogen double bond. But instead of having an R prime group attached to it, instead of having an OH group attached to it, it has the N R prime groups attached to it. And again, maybe that's NH2, maybe that's NCH3 maybe that's NH phenyl. A lot of correct things there. Now there's one reaction that we are not going to cover, but I do want to tell you it's going to show up on your PLO when you go through and fill out the reactions PLO. We can take these carbon-nitrogen double bonds and we can hydrogenate them. So we could take this with hydrogen on palladium, hydrogen on nickel, and we could reduce the imine, the hydroxylamine, the hydrazones. We could reduce them down to just amine or hydroxylamine or hydrazine again. So there's a lot of chemistry that comes back from the OChem1, the hydrogenation chemistry. I think we're just going to focus on these because we've got some mechanisms to do too. So rather than getting it too cluttered, let's do this. And then important to recognize that each of these is hydrolyzed. Back to a carbonyl with H3O+. So generally, you're not going to use an imine or an enamine or an oxime or a hydrazone as a protecting group like you would with an acetal. But it is important to know you want to protect its conditions. And I apologize, I just noticed that I kind of left this off on my last reaction, the same conditions that we're always used to seeing. All right, so let's do some practice, shall we? remove the two H's, just leave the third H. But since it's NH2 in HCH3, you're going to remove those two H's. And then the rest of this is going to be connected to nitrogen. Good, good. Now, can you provide the reagent that would take that in the reverse direction? Because that's also a thought I wanted to have. The last one. Yeah, but in the reverse now.
Oh, I see.
Yeah, yeah. So you did give it to me as the arrow was shown. Good. Good. Yes. Good job. Oh, actually, sorry. Well, you're missing one H up here. You have to show that H.
Oh, okay. That's not.
Can't be assumed. Hydrogens on heteroatoms can't be assumed. Sorry, I'm not trying to peer. Okay, so if we were going from here to here, that is exactly what we would want. However, notice that the direction actually takes us away from the amine, back to the ketone. So what reagent would we need in that case? And then here, we changed it from H. But notice that you don't have the second N. So you're going to have the N here on the left, connected to the N on the right, and HCH. All right, I'm going to put these up here. The first one forms a hydrazone because I have that 2 nitrogen group. The last one is actually hydrolysis of an imine. So as shown, I need to provide H3O+. But if I were going in the reverse direction, what would I want to have? I would want to have ammonia be present, and of course, some acid and molecular sieves. Now this last one, what is that functional group that forms? An enamine. That's an enamine. And enamines form because my nitrogen doesn't have enough hydrogens. So how can I be confident about where the carbonyl carbon is? Can the carbonyl carbon be on the right, or does it have to be on the left? So remember I gave you a tip with acetals and hemiacetals. I said that the acetal carbon is the carbonyl carbon. What about with this family of nitrogen functional groups? What carbon is the carbonyl carbon? The carbon that is attached to the nitrogen. Nitrogen here is a nucleophile. The carbonyl carbon, we said at the beginning of this whole unit, is an electrophile. So the carbonyl carbon is the imine carbon. The carbonyl carbon is the enamine carbon. So here's my enamine carbon. That's my carbonyl carbon. Notice that it's secondary. That means that it's going to be a ketone. Notice that this is primary. That means it's going to be an aldehyde. Notice that this is secondary. That means it's going to be a ketone. Let's try to do one quick synthesis problem. How can I go from one butene to this 2-oxime butane? Remember, it's always best to work forward and backwards. and I see the very final step clearly. What functional group should be here just prior to the oxine formation? Aldehyde or ketone? Ketone. And I'm going to react that ketone with hydroxylamine and acid. So now I need to get to that ketone, and I can actually do that in 2 steps. Anybody?
One would be to put 2 alcohols on the break the double bond with 2.
Okay, so like OSO4 to make a diol?
Yeah.
Okay.
And then with that, go back to the carbonyl.
Well, I don't know how I can make a carbonyl at position 2 and not make a carbonyl at position 1. Why do you want 2 alcohols there? Don't you want just 1 alcohol at that position, position 2? Yeah. And is there a way that I can selectively add an alcohol there and not at the other position?
Yeah.
What should I add? It's your most basic reagent. Sorry.
NaBH4.
NaBH4 would reduce this ketone to this alcohol. I want to create this alcohol from an alkene.
Can you do the, no, I don't know the name, but like the Hg acetic
Yeah, you could
acid?
oxymercuration
Okay,
reduction.
yes.
You could do that. There's no need to. The benefit of oxymerc reduction is that it adds Markovnikov and avoids carbocation rearrangements. So what's the other one that doesn't avoid carbocation rearrangements? Since I'm not worried about a carbocation rearranging here. It's the simplest hydration.
Water and H3.
That's right, acid catalyzed hydration. Adds it Markovnikov. And then from the alcohol to the ketone, what reagent could I add?
Like the chromium 03 H2SO.
Yeah, chromic acid in the form of chromium trioxide and sulfuric acid. What do you think? Not hard, right? Does take a little bit to get the gears turning. All right. Couple more reactions for us to consider. That was number 6, right? So 7, we're going to see acyl addition to a cyanohydrin. This is actually probably going to feel very simple compared to what we've been doing. So I can add cyanide in the form of cyanic acid, HCN, hydrogen cyanide. Remember that R here is allowing me to write a generic reaction for both a ketone and an aldehyde. So if I have a primary cyanohydrin, then I reacted with an aldehyde. If I have a secondary cyanohydrin, I reacted with a ketone. That's simple acyl addition, and it places both an alcohol and a nitrile onto the same group. Now, the next one I want to introduce to us it's going to seem a lot more complicated, but trust me when I say this is one of the coolest reactions you'll ever see. I did spell Bayer wrong. This is the Bayer-Villager reaction, but it's actually spelled B-A-E-Y-E-R. Just like Bay. What we need for this reaction is a peroxy acid and a ketone. So this is actually selective to ketones. We're not going to see this reaction with aldehydes. So in order to show that, I'm actually going to expand my carbon chain just a little bit more. And show that there's a carbon on both sides. Deal? This reaction is regioselective, meaning if the two carbons are not equally substituted, if it's not symmetric in some way, then the reaction will occur on the more substituted position. And I suppose I did misspeak. This reaction can be done on aldehydes. We're just not going to see it done on aldehydes. So of those two carbons of the ketone, is one of them more substituted? That's right. That's a secondary carbon, and that's a methyl group. RCO3H, that's just our generic way of writing peroxy acid. Oops, sorry. What is the conversion that we're seeing here? Ketone to an ester. Exactly. Isn't that kind of cool? So let me give you guys an example reaction here that demonstrates just how fun this is to look at. You guys remember one of our favorite peroxy acids? We learned it in OChem 1. We learned how to name it now in OChem 2. It's a peroxy acid that does epoxidation for us. MIGBA, MCPBA, metachloroperoxybenzoic acid. This is going to take a ketone and convert it into an ester. Which carbon will become the ester? Which side will become the ester? Anybody? I'll give you a hint. There's the one with the methyl. So let's say it adds either the secondary carbon or the tertiary carbon, which becomes the ester linkage. The secondary carbon or the tertiary carbon? Tertiary. I just wanted you to make sure you knew that vocab word. So, within a ring, I've taken this cyclic ketone and created a cyclic ester. Within a chain, I can take a linear ketone and make it a linear ester. Pretty cool reaction. Here I've got 5 in the ring plus 6. Here I've got 1, 2, 3, 4, 5 plus 6. I did draw it really poorly, and maybe what you're seeing is that it almost looks like a 7-membered ring. No, in fact, all it did was expand the ring into a larger structure. Isn't that wild? That's cool stuff. All right, and our last reaction here is called the Wittig reaction. Spelt Wittig, pronounced Wittig, telling you that it came from what area of the world? Yeah. Northern, Eastern European. I mean, Germany was a hub for chemistry for a long time. Now, the Wittig reaction and the Baeyer-Villiger oxidation, as you guys can tell, these are actually named after people, whereas the imine, the enamine, the acetal, those are named after functional groups. So if you can memorize the functional group, you memorize the reaction. What I would change the Baeyer-Villiger oxidation to is ketone oxidation. Yeah? I would take that and just say ketone to ester. The Wittig reaction, I would actually refer to as carbonyl alkene synthesis. I made that word up. But I think that's fair to make up words because all words are made up. And it kind of flows. It has a good ring to it, and it tells us exactly what we're going to see. If I take a carbonyl and I react it with a reagent called an ylide, that's Y-L-I-D-E, although I think some places leave off the E, and they just call it ylide. The ylide is a triphenyl phosphine, so that's phosphorus bonded to 3 benzene rings, that has a double bond to a carbon group. Then the product that we get is an alkene. And of course, there's a byproduct, and that byproduct is a triphenyl phosphone, where instead of being double bonded to the carbon, the phosphorus is now double bonded to the oxygen. And this is a very cool reaction. There is some stereochemistry that's involved here. Not every textbook is very good at explaining the stereochemistry, so we're not going to dive into that too much. Instead, we're going to look at fairly symmetric alkenes, alkenes that don't necessarily form E or Z isomers. Otherwise, you'll be shown an alkene, and you'll just have to be able to predict what possible carbonyl it could have come from. But there's interactions between this whole phosphorus group and the carbonyl oxygen group that can help actually dictate whether the E or the Z isomer is preferred. That's our Wittig reaction. You know, there is one last reaction I wanted to show. This, I'll be honest, I would have rather had closer to the ketone oxidation. And this luckily doesn't have a name. I just want to point it out to you. So we can call this the aldehyde oxidation. If I take an aldehyde and I react it in the presence of chromic acid, then I can turn that aldehyde into a carboxylic acid. In fact, when when alcohols are being oxidized into carboxylic acids, an alcohol will form an aldehyde carbonyl first before they form a carboxylic acid. A cool example of this is if you take methyl alcohol and you oxidize it with chromic acid. This will go through a series of different compounds before it finally bubbles out carbon dioxide and water. The first thing that it does is it oxidizes to an aldehyde, just like PCC, but aldehydes are also reactive to chromic acid. So then formaldehyde is oxidized into formic acid. And the cool thing here is that formic acid also an aldehyde, as indicated by the form part of the name. So formic acid gets oxidized a second time. Alcohol oxidized to aldehyde, aldehyde oxidized to carboxylic acid, aldehyde oxidized to carboxylic acid. You all know and love this reagent. This is what? It bubbles from your sodas. It's also in your blood. Helps balance the pH. No, you definitely don't want formic acid in your blood. We could call it methane dicarboxylic acid. That would be an IUPAC systematic name. But its common name is carbonic acid. So if you've got bubbles, if you've got a carbonated soda, you've got carbonic acid. And carbonic acid is not stable. It readily decomposes into H2O and CO2. So ketones can be oxidized through the Baeyer-Villiger oxidation. Aldehydes can also be oxidized with chromic acid. So you don't have to take an aldehyde down to an alcohol and then to a carboxylic acid. You can take an aldehyde directly to a carboxylic acid. All right. Now let's do just a few more practice problems, shall we? not made an ester. You also got rid of the aromatic ring. So it's either going to break the carbon bond between carbonyl and ring or carbonyl and methyl. And I think that what you were going for was breaking this carbon-carbon bond. But you never did. So you have to break that bond first. Good. No. There's no carbonyl down here. And yeah, this one's not right. This one, you have not made an ester. You actually broke a carbon-carbon bond in the ring.
Well, these are two separate bonds.
You broke a carbon-carbon bond in the ring. And you don't have an ester. You need to break a carbon-carbon bond between the carbonyl and something else. But you actually haven't broken the
So I
carbonyl
have to
bond.
put it like here.
Sure, but don't put it in the ring. If anything, draw the two fragments and then connect them by the
Okay.
Yeah? But think about the bottom one too. This reagent is the ylid. And notice how it brings the CH2 with it. So where is the CH2 of an alkene? It's here. Nothing's going to happen down here. Okay. So take this ring to an oxygen. There you go. Now take that oxygen to the carbonyl. Not quite. Too many carbons. Just one. Just straight to the carbonyl carbon. All right. So with the Bayer-Villiger oxidation, we're gonna create a ketone between the carbonyl carbon. Or sorry, we're gonna create an ester between the carbonyl carbon and the more substituted carbon. Carbonyl carbon to oxygen, more substituted carbon to oxygen. This gives me phenyl acetate from acetophenone. Down here, the ylid is bringing with it a CH2 group, and we know that the ylid is involved in carbonyl to alkene synthesis. So here is the alkene that has been synthesized. Where then is the carbonyl? It's at that position. So that is 4,4-dimethyl cyclohexanone. And then at the bottom one, I create a cyanohydrin product, which means that I want to add cyanide, HCN with H+. All right, we definitely don't have enough time to get through all of the mechanisms that I wanted to get through today, which means we're going to pick up there tomorrow, but I'm going to give us just a rundown. The mechanisms that you may see on this week's unit test and the mechanisms that will be on the final exam are the acetal synthesis and hydrolysis. So that means taking a carbonyl forward and backwards. From an acetal. And the Wittig reaction. Now, it would be just as easy for us to show the imine and enamine mechanisms, they're all fairly similar to the acetal synthesis. All you're doing is changing the nucleophile from an oxygen to a nitrogen. Actually, the VIDIG I have enough time to cover. The VIDIG is pretty short. So I want to show you guys how we can take benzophenone and we can react it with this smallest ylide, the methylene ylide, the CH2. And we can use that to form 1,1-diphenylethylene. Now the mechanism is actually so simple, it can be done in just 2 steps. It's all about lining up the components correctly. The carbonyl and the ylide are going to face so that the carbon groups are right by each other and the phosphorus and oxygen groups are right by each other. Now thinking about electron arrow movement, both double bonds need to break. Who owns the electrons of the carbonyl bond? Oxygen. Who owns the electrons of the ylide bond? It might surprise you to find out that it's carbon. In fact, there is a resonance form of the ylide where the carbon holds a negative charge and a lone pair, and the phosphorus takes on a positive charge. It might surprise you to see this because recognize that the phosphorus here has an octet. Phosphorus has 4 bonds, 3 to the phosphines, 1 to the carbon. And yet it takes on a positive charge. That's much like nitrogen. When you have ammonium, NH4+, nitrogen has a positive charge, but an octet. Phosphorus, though, is in the 3rd row, which means that it can expand its octet. So phosphorus can take on 10 electrons, 5 bonds, and that actually gives it a neutral charge. So carbon owns these electrons. So in the first step of this mechanism, oxygen attacks the phosphorus, carbon attacks the carbon. And that gives us this square intermediate. Not every textbook agrees on this mechanism, but remember that mechanisms are plausible. And there are other plausible ways. This is the plausible way that I find most enjoyable to think about. Now, we need to form a carbon-carbon double bond, and we need to form that oxygen-phosphorus double bond. So there are 2 more bond breakings that need to happen. The carbon-oxygen needs to break. Who owns those electrons? Oxygen. So oxygen takes those electrons to form the double bond. The carbon-phosphorus bond needs to break. Who owns those electrons? Carbon. And that's how we get to the carbon-carbon double bond. That's how we form our alkene. We have both a nucleophilic carbon from the ylide and an electrophilic carbon from the carbonyl. And they just go through this swap of their electrons. Very cool. So tomorrow, we're going to pick up looking at our acetal mechanism, and I think we'll have enough time. I'm going to demonstrate kind of how it applies to the imine reaction as well. Then we're going to dive into acid derivatives, and we're actually just going to put up one big chart that shows how all of the different functional groups interconvert between each other and all the reagents that are necessary. So instead of doing it like we have been with this list, I'm just going to give you guys one big graphic. And then we'll just do practice problems, another mechanism, and we'll get ready for our unit test, okay? All right, have a good night, and I'll see you tomorrow.